We're starting a unit on relativity. As part of it, we're going to be looking at Albert Einstein's theories of relativity. One is called special relativity and one is called general relativity. Really, they should be called special case relativity and general case relativity. And the special case is A is 0. If you don't allow things to accelerate, I can prove Einstein using Math 8. If you allow things to accelerate, the general case, general relativity, if you allow things to accelerate, that math is well beyond me. You have to invent an entirely new branch of geometry, and you got to dive into field equations, and it gets pretty ugly pretty quick. But we're going to start out, before we look at Einstein, just talking about what's meant by relative velocity. And so I wrote down here, lesson 1, relative velocity, or, hey, what happens when there's more than one object? And then I wrote, and graphing it becomes tedious. We used to solve these by graphing, and you would find where they crossed. Some of what you did last year when you solved systems of equations. Graphing, Caleb, is useful, but it's a pain. It's nice and visual, but it's just a pain to do all these graphs all the time, even with software. Here's the point, though. If you cross this part out for me, please, that last half of the sentence, you'll know you're in relativity. You'll know you're doing relative velocity because there's two objects. If there's two objects, that's a job for relative velocity. So I'd like you to use your imagination. Suppose you're driving down the freeway. Your speedometer reads 100 kilometers per hour. A Ferrari hurtles by you with its speedometer reading 180 kilometers per hour. Suppose a tow truck is parked at rest beside the freeway. What would the tow truck see? Let's go even more general. I'd like you to imagine you're on the freeway and you're doing 100 kilometers per hour, and right next to you there's a car that's doing the same speed as you are. Compared, if someone is standing on the ground, they'll see both of you traveling at 100 kilometers per hour. But relative to you, if that car is staying right next to you, how fast is that car traveling relative to you if it's staying right next to you? 0. Not just the same, 0. As far as you're concerned, both of you are at rest and the world is revolving around you. So we're going to try and use our imagination, Ajne, to put our mind into what would we see. The fancy term is, what's our reference frame? What's our reference frame? So the first reference frame here is a tow truck. And the key idea behind the tow truck is it's parked at rest. What would the tow truck see? So I'd like you to imagine you're sitting in the tow truck now, or you're the tow truck driver, and you go zipping by. What would the velocity of you relative to the tow truck be? I think it would see you go zipping by at 100 kilometers per hour. Wait. You can see that I wrote here VU relative to the tow truck, V Ferrari relative to the tow truck, V Ferrari relative to you, V tow truck relative to you. I wonder if there's a way that we can abbreviate that. We can. So at the very bottom of the page here, I wrote, Mr. Dueck, is there a short way to write this? You can write your 100 kilometers per hour, and if you wrote that, that's fine. But just to get you used to the notation, coming behind you, Chris. Thank you. I would write it like this. V, and it is velocity. Direction's going to matter here. U relative to the tow truck is 100 kilometers per hour. So we'll do the first person relative to the second object, and we'll show is relative to with an arrow. Is that okay? So if I wanted to write V Ferrari relative to the tow truck will see the Ferrari traveling at 180 kilometers per hour, because the tow truck, as far as it's concerned, is at rest. And this is how we normally think of things. Most of the time, Kath, our frame of reference is on the ground. We compare everything to if we were standing there. But what would you see? What would you see? I'd like you to imagine that the Ferrari goes zipping by, and so it's pulling away from you going forwards. how fast would you see it traveling? Not 180. 80. So V Ferrari relative to you would be 80 kilometers per hour. And I'm going to add one more thing. In front of the 80, if you can fit it, put a positive, a plus sign. Why? As far as you're concerned, you're at rest. And the Ferrari is just moving 80 kilometers different from you, because that's your frame of reference. You don't need to write that down as a paragraph, but why? We just did it verbally. What about the tow truck? Well, if the tow truck was in front of you, you would see its back end getting towards you. Once you passed it, in your rear view mirror, you would see its headlights retreating away from you. What would you see the tow truck as traveling? I'm going to tell you, not 100 if I'm very fussy. Negative 100, because as far as you're concerned, if an object's backlights are coming towards you, it's in reverse. Or if an object's headlights are moving away from you, when you're looking behind you, it's in reverse as far as you're concerned. So you would see the tow truck relative to you retreating at negative 100 kilometers per hour. Got to use your imagination a bit here. But certainly, if you see backlights in front of you getting towards you, normally you would say, oh, that vehicle is in reverse. Here it's not. Well, yes, it is. It all depends on your frame of reference. What would the Ferrari see? So the velocity, I should have a vector sign over these because it is direction matters, of me relative to the Ferrari. Okay, when the Ferrari is behind me and gaining on me, it sees my rear lights coming towards it. Zoom, it goes past. When it looks in the rear view mirror, it sees my headlights retreating away from it. How fast does it see me traveling? The magnitude is 80, but what direction does it see me traveling as far as it's concerned? It sees me traveling at negative 80 kilometers per hour. And the velocity of the tow truck relative to the Ferrari, it sees the tow truck traveling at negative 180 kilometers per hour. So Einstein looked at this and he asked, which one of these is the correct answer? Which of these is the actual answer? And after he thought about it for a while, and we'll get to this in a few days, he said, you know what? You can't prove that any one of these is correct or incorrect. They're all correct, depending on your frame of reference. There is no experiment in the universe that can show that one object is at rest when another object is moving. There is no experiment in the universe. So you might say, I'm moving in the car and the earth is at rest. There is no experiment in the universe that can show that the earth isn't moving and that the car isn't at rest. When we accelerate, those we have experiments that can detect that. But if you're going at a constant speed and acceleration is 0, all of these answers are right. In other words, it's all relative. One of the reasons he used relative and relative velocity. So you don't perceive the Ferrari to be moving away at 180 kilometers, but at 80 kilometers. And because it's going forwards away from you, you perceive it as traveling forwards. The relative velocity of any object depends on your point of view or your frame of reference. Sure, you see the car moving away at 80, but the other driver sees you moving backwards at negative 80. You may have experienced this. How many of you ever walked on one of those moving walkways at airports? Okay? Where you look at the people that aren't using the walkway, and relative to you, they seem to be retreating very, very quickly, but you're not walking as fast as they're retreating because you're also getting a speed boost from the moving walkway. Example 1 says this. What's the relative velocity of the train passenger relative to the person on the ground in each case? So my abbreviation for relative velocity is VREL. Relative velocity. What does this person on the ground see this person walking at? And I'll give you a hint, not 1.2. What does this person on the ground see this person walking at, as far as they're concerned? Not 15. Kathy. And to the right, let's call that positive. Positive 16.2 meters per second. The person is walking at 1.2, but the train is moving at 15. As far as the person on the ground, the farmer on the ground is concerned, that person just walked past them at 16.2 meters per second. That's the effect you get on the moving walkways at the airport too. I don't know about you, I'm still childish enough. I thoroughly love walking on those moving walkways, and I get a childish delight watching the ground go zipping past me as I'm walking, to me slowly, but wow, it feels like I'm walking really fast, like a little superpower. What would the relative velocity be here? 13.8. Still positive. What if, first of all, this train car was really long? And what if this person sprinted to the left at 15 meters per second? What would the farmer see as their relative velocity if they were running this way at 15 meters per second while the train was moving this way at 15 meters per second? As a number exactly? 0. Really? So you're saying if we had a car that was moving to the right, let's say at 60 miles an hour, because the video was made in the US, and we fired an air cannon with a soccer ball out the back at 60 miles per hour, the two velocities would exactly cancel out? Put your pencils down. Look up. So, what are some relative velocity questions? And by the way, from now on, we're going to mostly use relative speed. I'm not going to be fussy as the positive or negative. I'm just going to say, what's the combined velocity? A zebra is running away from at 50 kilometers per hour from a cheetah going at 90 kilometers per hour. What velocity does the zebra see the cheetah as having, and vice versa? So from the zebra's point of view, velocity of the cheetah relative to the zebra looking over its shoulder sees the front part of the cheetah getting closer and closer and closer. So as far as the zebra is concerned, the cheetah has a positive velocity, but not 90. What would the zebra see the cheetah as traveling? 40. What about the velocity of the zebra relative to the cheetah? Well, the cheetah sees the hindquarters of the zebra getting closer and closer and closer. So as far as the cheetah is concerned, the zebra is backing up towards it. Now you're going to say, well, that's not what's happening in real life. Einstein said, prove it. It is what's happening in real life depending on your frame of reference. So what does the cheetah see? A negative velocity, and how big? How big? Yeah, 40. I'm not going to be fussy on the positive or negative. I like question C, I like question C, I like question C, but we're just going to use relative speed for question C. And what I mean by that, Ajne, is don't freak out about the negative or positive. Just get the 40. So here's the question. If the zebra starts out 90 meters ahead, how long will it take until the zebra catches up? And this is important. Please underline this. For all relative velocity questions, for this entire unit, we're going to assume that A equals 0. A equals 0. If you bring acceleration in for relativity, that took Einstein 10 more years to figure out, and we're not going to dive into that. So, what's this question asking me to find? Good. They just told me A equals 0. What's that 90? How do you know? Okay. What's that 40? So you ready? We're going to use that 40, the relative speed between them. There is an equation that has a T, an A, a D, and a VI in it. Which equation has a T, a D, an A, and a VI in it? You probably remember this one. I'll give you a hint. It was D equals... Which one is it, Caleb? Okay, so you ready? We're going to modify it just slightly. So it starts out like this, but what's your acceleration in all relative velocity questions? So that whole thing vanishes. And if you're not speeding up or slowing down, your V initial is your V final, is your V relative. In other words, here's the modified version that we're going to be using for this unit. D equals relative speed times T. Did I put that on your formula sheet? Nope. Did I show you how you can derive it? Yep. I want to get the T by itself. Rob, what's the V doing to the T? Adding, subtracting, multiplying, or dividing? If there's no sign in between, that means times. So how will I move the V over? What's the opposite of timesing by V? So are you telling me that T is going to be D divided by V? Yes. Robert, what was D in this question? 90 what? Oh, got a small problem. Next to the 90 where we listed our data, let's put an M for meters. What are the units next to this 40? We don't do physics with kilometers per hour. We need to do a conversion. How do I go from kilometers per hour to meters per second? It was something to do with the 3.6. Does it divide by 3.6? So 40 divided by 3.6, and I get 11.1 repeating. So it's going to be 90 over 11.11111. I'm going to use my answer button. How much time? I get 8.1 seconds. So if shelter is 89 meters away, this zebra might survive. If shelter is 91 meters away, this zebra is in trouble in 8.1 seconds. Now, maybe the cheetah can only sprint for 8 seconds before it tires out. There's this dance that occurs between predator and prey. Most of the time, predators can sprint really fast for short times. The prey can run away slightly slower, but for longer times. And it's where they meet that lunchtime happens. Nick and Cole are having an argument at an airport on a windy day. Nick says that airplanes should take off with the wind. He says that way the wind pushes them from behind and the planes will travel faster down the runway. Cole says that airplanes should take off facing the wind, into the wind. He's not sure why, but it kind of makes sense to him. Who's correct? Is that a suggestion? Into the wind? Why?
It generates more lift over the wings.
Why?
If the wind is going faster into the wing.
Ground speed has nothing to do with flying. Airspeed makes the difference. And if you go, airspeed makes the difference. If you go into the wind, you're getting an instant boost of air. In fact, if you're at rest but the wind is blowing at you, you're not at rest relative to the air. You're already moving relative to the air. Okay? Put your pencil down, look up. Video that you just saw, what was the speed of the plane relative to the ground? The ground was 0 meters per second. What was the speed of the plane relative to the wind? The wind was takeoff speed. Whatever that was, I don't know, but I can tell you, as far as the plane was concerned, it was traveling through the air. State the relative speed, it says, in each case. Here are two trains, one's going 40, one's going 40. Relative to each other, how fast are they traveling? Don't overcomplicate it. If they're both going at the same speed, 0. One's going 40, one's going 20. I don't care about positive or negative, which is why I'm saying relative speed. How fast is their relative speed relative to each other? Loud and proud. 20. What if they're heading towards each other? What's their relative speed? Nope. Good guess, though. We're not going to worry about negatives and positives. It's just speed. What if they're heading towards each other? And this explains why head-on collisions are worse. Nope, not 0. 60. Robert, what? 60. Anytime you give me a question with two moving objects, I refuse to do it. I'll let one object in my mind stand still, and I'll just move the other object with the relative velocity or relative speed. So you're going to be, on this next test and in today's homework, having two objects moving. You'll never deal with two objects at the same time. Use relative speed, and don't worry too much about the positive or negative unless it specifically asks for direction. Let me show you an example of what I mean. I like example 5, I like example 5, I like example 5. Example 5 is a nice question. Why would I say that? Did you hear me say it's going to be on the test, or you're the kind of student that notices when a teacher tends to emphasize certain things? Good, 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 good. Caleb, what's example 5 asking me to find? Okay. For relative speed or relative velocity when there's two objects, what did I say A is always going to be? Yeah, we could handle an A. We're not going to bother. Okay. We're going to use relative speed, VREL. What's the relative speed? One train is traveling to the right at 13 meters per second. One train is traveling to the right at 5 meters per second. What's their relative speed? 8. What if they were heading towards each other? What would the relative speed be? Not 8, but 18. What if they're heading away from each other? Also 18, because they're getting apart fast or they're coming towards each other fast. This is why head-on collisions are so much more dangerous, okay? If you rear-end somebody, what makes a difference is just your relative velocity. If you head-on somebody, it's also your relative velocity, and then they add together. So what did you say the relative speed was, Thomas?
8.
And then the last thing we want to figure out is the distance. Now, it says, how long does it take these trains to completely pass each other? I'm going to argue that to pass each other, the back part of this train has to get all the way past the front part of that train. How big a distance does it need to cover relative to the other train? I know they're both moving. I don't care about that. We're pretending that this train is standing still now. We're using 8 meters per second. How big a distance does it need to cover? Yep. Robert, is this 250 in meters? Say yes. And is this in meters per second? Say yes. Do I need to do a conversion this time then? Good. By the way, this is the famous, you hear this all the time as a math word problem. A train leaves Chicago heading towards Los Angeles at blah, blah, blah. Another train leaves Los Angeles heading towards Chicago at blah, blah, blah. How far did they go? When did they meet? You don't do it that way. We're going to do that question later on today, and we're going to use relative speed. We'll pretend one of the trains is standing still. I'm looking for an equation that has all of those in it. It's going to be this. What happened to the plus a half at squared? A is 0. Robert, what am I trying to get by itself? What's the v doing to the t? Adding, subtracting, multiplying, or dividing? So how do I move the v over? Yes. T is going to be, the distance drops down like a domino. There's a v underneath there. You can do this question with both of them moving, using systems of equations, using x and y and finding where they cross. Ugh! So much nicer to use relative speed. It's going to be 250 divided by 8. I think I can do that in my head. It's going to be 125 divided by 4. It's going to be 72.5 divided by 2. 37.5? Double check me. I'm off? 31.25. You're right. Divided by 8. Wow. I'll go 31.3. I'll go to 3 sig figs seconds. Okay. Dakota, how do you know this is a job for relative velocity? Can you read me this sentence right here? Are there? If there's two different objects with different speeds, that's a job for relative speed or relative velocity. That's your trigger. And what will the acceleration be then? 0. Okay? A couple more, we're done. Yep, we're good. Suppose you're at a local airport and you encounter a moving walkway. Now this walkway is 85 meters long and it has a speed of 2.2 meters per second relative to the ground. We would have until today just said it has a speed of 2.2 meters per second because until today we measured everything relative to the ground. What I'm saying to you now, Caleb, is we got to be careful. If it takes you 68 seconds to cover 85 meters when walking on the ground at a constant speed, everybody underline the word constant speed. If I say constant speed, what's my acceleration? Okay. Part 1. Chris, what does part 1 want me to find?
Your walking speed.
V equals question mark. A is 0. What's that 68?
Your T.
What's that 85?
T.
Looking for an equation that has an A, a V, a D, and a T in it. There is one. It's just going to be D equals VT. What happened to the plus a half AT squared?
A is 0.
Yep, and Einstein said, what if I bring A in? That was 10 years of hard math later. We're not going to get into that, but we'll talk about why it becomes so much more difficult. What am I trying to find?
V.
We'll get the V by itself then.
Divide T.
So it's going to be 85 divided by 68. Here's my walking speed. Do you get 1.25? Units, Chris?
Meters per second.
Okay. This is my walking speed. Remember the picture of that guy with the pack on the train that we did earlier? He was walking, I think, at 1.8 or something like that. This is me walking on the train, but instead of the train, it's the moving walkway. But if you're looking for an analogy, okay? How long will it take me to cover 85 meters on the walkway? Okay. Well, first question, what's this wanting me to find? Time? Is there more than one object moving in this question at different speeds? Yes. This is a job for relative speed, so my acceleration is going to be 0. Looks like the distance that I need to travel is 85. Here's the question. What's my relative speed here? Yep. How'd you figure that out? in your homework, if you just go 3.45, I'm good. In our notes, let's write down that we went 2.2 plus 1.25. And you said 3.45. And those are all meters and meters and meters per second. We're happy units. Okay. I think we're going to get Rob's equation, right? Rob earlier gave us D equals VT, and you said to get the T by itself, we would divide by V. D85 divided by 3.45. How many seconds now is it going to take? 24.6, is that right? How much time did it save me? How long would it take me to walk 85 meters on the ground? 68 seconds. I did it in 24.6. If you don't think that airports haven't calculated that out and they've realized this allows them to get jets off faster, because it costs them money to build those walkways. They didn't build them to be nice to you. They built them because if they can save you time getting to your next gate, that lets them get more jets in per hour, and that's millions of dollars in profit. There's no way. Have you ever thought about why do they build those walkways? It was not to be nice because you're tired coming off a plane. If you think that, you haven't understood airports, because sitting on the plane in those hideous seats, are they making those seats bigger or smaller over the past? They don't care about your comfort at all. It's all about profit. Those walkways are all about profit. That's a huge time savings. That adds up like crazy. Just for what it's worth. How many of you have been on one of those walkways before? How many of you have done B? Get on the walkway, turning around, and start walking in the opposite direction so you're going against the grain. Okay, as long as there's no traffic, as long as you're not ticking people off, I encourage you, if you have time, try that too, because you'll get a strange feeling. Your body is telling you you're hustling and walking really fast, but when you look over the railing, you're barely going anywhere. Or you might even be walking forwards and going backwards, and your brain doesn't quite know what to do with it. So, what's your new speed relative to the ground? I'll give you a hint. Not 3.45. What would it be? How would I calculate it? How'd you figure that out? You went like this. 2.2 minus 1.25. And I'm still moving, I'm still traveling forwards in distance. I'm facing backwards, but I'm still gaining distance. I'm walking backwards, if you want to call it negative, because I'm able to. Oh, no. The walkway's faster than me, isn't it? I would be going backwards. I'd be facing the rear of the walkway, but I'd be traveling. My back end would be moving forwards relative to people on the ground. See, it's all relative. I have a difficult time giving you direction without saying, compared to what? Because as far as I'm concerned on the walkway, I'm walking forwards, my feet are facing forwards, and I'm gaining this way. So how long would it take me to cover the 85 meters now? Time is going to be distance divided by speed. Is that right? I dropped down the same equation that Rob gave us, I think. Still 85 meters, but now my speed is 0.95. Instead of doing it in 24.6 seconds, it's going to take me 89.5 seconds. Is that right, I think? Austin's looking puzzled. D over V? Or did I type it in wrong? Is that right? 89.5? Yeah. I like example 4, I like example 4, I like example 4. Example 4 is a nice question. Example 4 without relative speed is very, very difficult. With relative speed, it's not plug and chug, but it's close. The police are in hot pursuit of a car. The car is 320 meters ahead, and it's going 150 kilometers per hour. If the police are going to ram the car in 20 seconds, what must be their velocity in kilometers per hour? What's this question asking me to find? James, what's this question asking me to find? Is there more than one object moving? Are they moving at different speeds? Then I'm going to say you're wrong, sort of. You know what it's really asking me to find? Relative speed. That's what we're going to find. Then we'll unrelative speed it, if that makes sense. Is there more than one object moving in this question? Are they moving at different speeds? What's my acceleration? Because that's what Mr. Dueck has said will be the case. What's that 20? James, my friend. Yeah. What's that 320? What's that 150? Ignore it. Because if they're asking me to find a velocity, there's two objects moving, I'm going to find a relative velocity or a relative speed, and then I'll come back to that. I'm looking for an equation that has a v, an a, a d, and a, you know what? It's this one again. D equals vt. What happened to the plus a half at squared? And what happened to the initial? Well, if there's no acceleration, your initial is final. In fact, what you're finding here is going to be just the relative constant speed. How would I get the v by itself? It's going to be 320, and that's meters, divided by 20. That's second. This is going to give us an answer in meters per second. What do you get? 16, I think, if I do the math in my head? Dakota nodded? Yeah? Okay. That's the relative speed. Now, let's see how fast it's going to be in the quote-unquote real world. I noticed they gave me this speed in kilometers per hour. So what do you think I should convert this 16 meters per second into? So let's do that. How do I go from meters per second to kilometers per hour? So what do you get? 57.6? That's how fast the police would need to be traveling if the bad guys were stopped. Are the bad guys stopped? How fast are the bad guys traveling? So the police are going to have to travel this much faster than the bad guys. If they were stopped, you'd go 0 plus 57.6, which is 57.6, kind of trivial. So the police is going to be 57.6 plus 150, and these are both kilometers per hour. Here, we calculated the relative speed and we knew how fast the bad guys were. Police radar detectors that are mounted on cars, they would know how fast the police car was traveling relative to the ground. They measure your relative speed and they use that to calculate how fast the oncoming car is coming. But it's the same procedure, not much more difficult. I mean, okay, they're flashing beams of light, and that's how they're getting time, and that's a nice little microchip, but in terms of the math, same thing here. Okay. What's your homework? There's only 10 minutes left, but in the next class, when do I see you next? Today is Tuesday. Thursday, you won't be getting new homework on Thursday, so you can tide this over for the weekend if you want. I'm going to give you a fair bit to practice. So number 1, number 2, 3 is good, 4 is good, 5 is good, 6 is good, 7 is good. I'm going to assign most of these, but not all of these. Maybe I'm going to assign all of these. 8, 9, and 10 are good. 11 is good. I thought there was a question that I didn't like. Maybe I nuked it finally. Never mind. 12. Yeah, all the questions, because I got rid of the questions I didn't like.